So I want to thank Amir and Asad for organizing TDLS and for giving me the opportunity to present the work here. And the cool book I've read, rather I have listened to, or I'm listening to right now, it's called Dark Pools. And it's about how high-frequency trading came to existence, and it's talking a little bit about the dot-com crash around 2000 and how high-frequency trading was involved in it, and various flash crashes. I can highly recommend it. And today we're going to talk a little bit about backpropagation. So backpropagation is one of the key, or if not the key component for building neural networks or larger neural networks. And for those in the audience who are not very technical, I have to tell you this is rather a more on the heavy side with equations and formulas. But my promise here is I'm going to take you by the hand and we're going to go through step by step. And if you have any questions, you can just raise your hand and we're going to clarify it. So a little bit about myself. So I did my undergrad in Munich at the Ludwig Maximilian University of Munich, followed by a PhD at the Technical University of Munich. Both of them were in bioinformatics, which was heavily on like data science, data analytics, machine learning, heavy, and a lot of algorithmic and software engineering. Then I did a postdoc at U of T with Gary Bader and Andrew Emily, with focus on predicting protein-protein interactions like machine learning on networks and graphs. And then I joined Zero Gravity Labs, which is the innovation think tank of Loyalty One. And their premise was to basically get like the smartest and best people together and do the innovation of their own business, kind of disrupting themselves to be on edge with changing markets. And after that, I joined BMO Capital Markets, doing trading, algo trading for US Treasury bonds. And my current project, I'm going to do some data scraping and natural language processing on like mixed data documents, kind of quarterly annual reports. So, as a rather old baby from 1986, if I remember correctly, I was born in the same year, and Geoffrey Hinton was already busy developing neural networks at the time. And it was funny because someone told me he did this backpropagation, and then he was around in New York, so he went to Canada, and he said, oh, in around 2000s, I'm gonna do neural networks, going to be really big, because back at that time was kind of like an AI winter, and neural networks were not popular at all. And he said, oh, I'm going to figure that out, I'm going to make this viable, I'm going to be a big thing, just takes me 5 years. Well, it took him 12 years, but now we are here, and everybody's talking about neural networks. And basically, this is how it all started. And if you see the paper itself, it's really short, maybe 2.5 pages. And if I would just simply go through the paper and say, okay, here are the equations done, that would be like a 5-minute presentation, and nobody would be wiser. So I said, okay, I'm going to make myself a promise, and I'm going to take you all through this step by step, so in the hope that everyone will get and understand what's backpropagation. So a little bit about the terminology. So X is the input matrix. So this is kind of the data that comes into the neural network. And basically what's happening is these kind of data gets transformed and modified using weight matrices. So they are denoted with W. And once I apply the weight matrix on my input data, I reach a hidden state, which we call Z. And on the hidden state, I apply some type of activation function. And the activation functions, after this, I will transform my hidden states to so-called activations, basically the output of the neuron. So basically, what you say is a simple perceptron, or a simple neuron, is here denoted with f of x, which is this, we multiply the weight matrix of the layer L with the x, or the incoming data that comes in, and then we apply an activation function. And what happens if I want to say, okay, I make a deep neural network, so I want to have multiple layers, layer after layer. So I like repeat the multi-layer perceptron. So it's just repeated application of the same function over and over again on the data. So you have to think of it like it's just this applied over and over again. And why do they want to use activation functions? So if you don't have an activation function in this step, well, what is happening? You just take this input x and then just apply multiple matrix multiplications repeatedly after another. And in that case, I'm not gaining anything, any information or any weight by doing this. I just can do linear combinations of the weight. So to ensure that I can capture nonlinear relationships, I need to apply some nonlinear functions on my data. So one characteristic of these activation functions has to be nonlinear. And as you later see, or rather, if you do a lot of machine learning, you realize these neural networks became huge. Like they have millions and millions of parameters. Now you want to apply this activation function a million times. It should be rather fast and easy to compute. Else you spend a lot of time just calculating these activations. And for the backpropagation, we need to calculate the derivative of the activation function. And of course, you want to have an easy derivative. The activation function I'm going to through here in this example is the sigmoid activation function. And what the sigmoid activation function takes here, denoted with blue, it takes your input data, which can be like between minus infinite and plus infinite, and it squashes it between 0 and 1. You can think of it a little bit like probabilities. So it takes some really large value or really small value or some random value and squashes into a probability. And if my value is less than minus 5, it's 0. And if it's larger than 5, it's actually almost 1. And everything else happens here in between. And if I have a value of 0, I have get a value back of 0.5. And the beauty of the sigmoid function is that the derivative of the sigmoid function is just the application, a combination of the values of the original calculation. So if you see for the forward pass, you're going to use the activation function. So this sigma of x, you already have these values in your memory. So if you want to calculate the derivative, you can do it super fast. You just multiply what is in your memory times 1 minus what is in your memory. And this is the big advantage of the sigmoid function. And now we go to forward propagation. So forward propagation, as described in the paper very beautifully with two equations. If you recognize this is a bit like the one-row matrix multiplication, and this is the sigmoid function. So I'm going to go through what happens here. So this audience might already be aware of this, but I'm going to do it for repetition's sake. So most machine learning problems, you have like some kind of input data and some targets you want to predict. So basically, this would be your features, and you try to predict your target. So the neural network is trying to reconstruct this target given these observations. And what's happening is you can write this data in this kind of matrix notation. And this is a very typical neural network representation. So you have the input layer, you have the hidden layer, and you have the output layer. And what happens is that the data moves through the neural network from the input layer to the hidden layer to the output layer, creating your final prediction. And what's happening is we have these 6 neurons, and they're going to create 3 hidden states. And what happens is basically for each hidden state, I have one weight, and I multiply it with another weight for the second dimension, and I take the summation of these. So you have to think of it as like a weighted combination of these two values. And now I have my hidden state.
What is the superscript?
The what?
The one on the top of W?
Oh, this is layer 1, basically. So this describes layer 1. These are the weights of the first layer. And these are the hidden states of the first layer. And now I want to apply the activation function for each of the states. And then I get my activations for each of the hidden states, the hidden neurons. And as described at the beginning, to reach the next state or the output state, we just repeat the same process over again. So we make a weighted combination of these activations. And then apply our sigmoid function to get the hidden state, and then we get our activation. And for the next data point, we just repeat the same procedure. And so these weights are initialized with random values. So they're kind of normal distributed with a variance of 1 and mean of 0.5. So they're somewhere between minus something, minus 0.5 and 1.5. But most of them are around 0.5. And the way these random weights are optimized to make a final prediction, we use gradient descent. And gradient descent utilizes derivatives. And if you remember from calculus what a derivative is, essentially it describes the slope of the function at a certain point. The way we treat the cost function is mostly a convex function, which means it has this kind of U shape, so it has a global minima. And when the derivative has a positive value, all you have to do is move to left to go down the slope. And if the derivative has a negative value, you move to the right, you walk down the slope. And the goal of the gradient descent is to find this point. And if you would start here, because this function is not convex, it doesn't help that much, but if you would start here, you would do gradient descent all the way to the bottom, and then here you get a positive derivative and you would walk back. And then at one point you would say, okay, I stopped learning, I'm somewhere here at the minimum. And as you see later on, we have multiple weights for each neuron. And we want to optimize each neuron individually. So we have to do partial derivatives for each individual weight. And what does a partial derivative mean? Let's say I have a function f(x) of y, which has two input and has this shape. And I want to do the partial derivative of this function in respect to x. The output would be 2x plus y. And if I want to do the partial derivative in respect of y, I have y plus 2y. And what happens if you take a partial derivative is that I take the parameter I'm derivating against as a variable, and all the other ones I treat as a constant. So here I treat y as a constant, and here I treat x as a constant. And for our input, we have like big multidimensional matrices. And what happens is that you treat all the other weights as a constant if you derive against one weight. And the weight you're deriving against, you treat as a variable. And another important part is the chain rule. Let's say I have two functions, and one function is the input of another function. So I have like composite functions. And I want to calculate the derivative x of the composite function. I can write this derivative in respect of the derivative of the functions. So I say, how much does this z change in respect to y in regard of y changing to x? So you cannot say, how does z change in regard to fx, but you can say, okay, how does z change in regard of y, and how does y change in regard of x? And that's why you can calculate the derivative of x against z. And the other ways of writing is like with this prime sign. And we went through this again. So gradient descent, essentially I start at a certain point. My weights are random, and I have a convex function. So the function has a shape like this. And because I initialized with random weights, I land somewhere here, anywhere. Literally, I can land anywhere for the sake of the argument. And I calculate the derivative. And the derivative tells me, okay, now I need to move right. So I'm going to move right, and I'm in a better cost. This is my cost function. I want to minimize my cost function. I want to have the best possible neural network. And in this state, I'm better than in the previous state. So I already improved my neural network. And in the next iteration step, I just calculate the derivative again, and I walk towards it. And then I'm here, and most likely, ideally, I realize this is the best point, and I stop walking, and I'm here in my global minimum. Most of the time, this is not true, though. And there are many ways of dealing with that. So this leads us to backward propagation. So how do we get these gradients, and how do we do these gradients to optimize our neural network? And the key player here is basically cost. So I have my input, I run it through a neural network, and I get some kind of random predictions out. And there's a difference between my random prediction and the real value I want to observe. And this difference we call error. And we want to minimize this. This is my cost function. This is the one I want to minimize. And of course, the total error of the neural network is just the summation of all the data points. And what do my weight matrices look like? So in the first layer, I have 6. In the second layer, I have 3 weights. And now I want to calculate the partial derivatives of the weight in regard to each individual weight. So for this cost function, I want to take the derivative against this weight, and so on and so on and so on. And when you start with the backpropagation, you start in the last layer. But the last layer is the most easiest layer to calculate the gradient on, since there are no other later nodes who can inherit the error from you. So you only have to calculate how does my neuron affect the error, the output, instead of how does my neuron also affect the other neurons. This is here very good and nicely summarized in 4 equations. And it starts all with this. What's my cost function with respect A2, my output, my activations of the last layer, in regards to my weights. And if you remember the chain rule, so my last weight is nothing else than a sigmoid of the hidden state. So we can say this is my g of x, and my f of y is my cost function. And now I can calculate the partial derivatives, apply the chain rule on this, which will look like this in this formulation, and will look like this using this fractal description. But what is this? This is nothing else than the sigmoid of the hidden state again, right? So now I can apply the chain rule again on the sigmoid function against Z2. And this apply this chain rule again. So first I'm going to show you how this is calculated. This is just the derivative of the sigmoid function. Step by step. So this is my cost function. And what happens, we apply the chain rule, so this part comes here. And we have to multiply the inner function with the derivative of the outer function. So this comes over here. Move this away, and then we have the inner function multiplied with the derivative of the outer function. And we do, the important thing here is we're doing partial derivatives, right? So for xy, if I do the derivative against xy, it has a certain value. If I do the derivative for I against any value that is not j, it's 0, right? I treat it as a constant. And then it's two constants I'm doing the derivative of, it's 0. And in the cases where I equals j, it's -1. It's very simple. Derivative constant minus the variable. So now I just plug it in here. So this is the derivative of this. This is just the derivative of the sigmoid function. And now we have to deal with this really ugly derivative. It's like this hidden states against weight matrices. And this is also called as not the error, but the way it describes basically how wrong your model is. This is the derivative of the error. So let's say, let's take Z2 like the last layer against the weights of the second layer. And how does it affect? There's a typo, this should be A1. So, and you're just looking at this part. So these weights, these activations get multiplied with the weights, creating this function. So we want to calculate the derivative of this, what's inside the circle. And we do partial derivatives. So let's say we first want to take a derivative against W21. So a neat trick is, since these are all constants, right, and this is just summation, and the derivative of summation is like the derivative of each individual term of the summation. So we just treat all of these, we just summarize them together as S, as one constant. So we say, okay, this equals to the derivative of S plus A11 times W21 against W21. And it looks very similar with what we've seen before, right? So this is again a constant, so it just, you don't care. And it's A11. And this is A12 for the next weight. So the partial derivative of this is just A11, A12, A11, A12, and A13. And what is happening is if I have a very large activation in the previous layer, I inherit most of the error from the larger activations. And thus I have to backpropagate most of the error back to these layers. So if I have bigger input from this neuron, I just give him more error. The idea is if a weight or the activation is 0 in the previous neuron, then and my target is 0, then I didn't inherit anything error, right? And another way of writing this is just to take the transpose of the A1 layer. So I take the transpose of the previous activation layer. So these are a scalar. These are just one number, and this is a transpose of the activation, A1, and it will be the same dimension as the weights. So this whole equation I add on the gradient. So if it's negative, I'm going to move to the right, and if it's positive, I'm going to move to the left. This is a summary of these equations. And now we have to do the more tricky part. So how do I do the derivative of a middle layer function? It's tricky because if I think about the derivative of this neuron does not only affect himself or the output, but it also affects the neuron it directly passes to, and the neurons after that. And the way they solved it is to be very lazy about it. So when we calculate the derivative of the function, we say, okay, I just care about the error of the next layer, and then when I'm calculating the derivatives or the gradients of this layer, I just pass it on to the next layer and so on. So having kind of like a procrastination approach to this problem, else it's just too much overhead. And what is the error of this layer, essentially? We calculated before, right? This was the last layer in our case. And how many neurons I have? K neurons. So I sum up over the K neurons the cost function derivative against that L plus 1. And then I need to calculate the derivative of the current layer. How this current layer affects the next layer. And we have calculated this already, right? So this is our error, our gradient error from the next layer. We just summed up. So now we just need to solve these derivatives. If you go into the core of it, what is ZK plus 1? It's just the sum of all the neurons Z times the weight. And A is just the sigmoid of the Zi, right? And we are calculating the derivative of J. So if I it doesn't equal J, the same holds true again, and the whole part becomes 0. So we just need to solve it for I equals J. So this whole summation goes away again, which is very convenient for us. And we have to take the derivative of this thing. And let's see if I have it here. Yeah. So it's just the derivative of the sigmoid function again, multiplied against the weights. So this is a multiplication. It's not affected by derivative, so you can just put it in the front. And it's just the derivative of the sigmoid against its input. So it's just the first derivative of the sigmoid function, for those who don't see it. This is not a very nice equation to deal with for most people. But if you have an I for it, this is just one row, 1 point multiplication in a matrix multiplication. So if you multiply two matrices, you multiply the column or the row of one matrix with the column of the other matrix, you get this one value. And if you would do it over all possible matrices, you have two summations. So you're missing for one part if you do it for one neuron. But what you're going to do if you want to do it for all neurons, you can just rewrite the whole equations, and you get some really nice matrix multiplication solution. which essentially I multiplied the matrix for each of the neurons from the next layer with the weights of the next layer transposed with the derivative of the sigmoid function of the hidden activations. And this gives me this error gradient. And if you plug it into this formula, we see this happening over again, right? We saw it before for the first layer. And we have to calculate the derivative of the hidden state 1 in respect to the weights 1. And what was it before? It was the transpose matrix multiplication of the input layer, the activations, right? But here we are at the first layer, so the activations are actually x or data input. So we have to multiply the x transpose against sigma 1. And you see all these terms are always in relation to basically the previous layer. And if you do the back propagation or calculation, you can just propagate the error back, and you just repeatedly just apply these functions. You apply first the one for the last layer. Oh, this is any layer, sorry, just written out. So you first apply it for the last layer, and then you get these, and then you use these to just calculate it iteratively for each middle layer until you reach the input, and then you have your input. What does happen if I do multiple batches or multiple data points? I run this through my neural network for the backpropagation. So each of these data points or batches generates a gradient, and in regards to the space of my weights 2 and weights 1 in regards to the cost function. And I'm somewhere here in this kind of hyperplane. And each of these data points is going to create a gradient to tell me, okay, you have to go this way or that way or go this way. And there are many ways of combining the gradients of multiple batches. But if you run it like, say, one batch already contains multiple data points, it tends to be just the summation of all the gradients. So you just go down. And from reading the paper, there was one really nice caveat I want to share with you. So the problem is, there are some before gradient descent, people used Newtonian methods or second derivative methods. The power of the second derivative method is that it shows you in a direction where is the global minimum, and you can just jump right into that direction. And it can help you to optimize much faster. So that in that regard, gradient descent is slower, and you have the risk of being stuck in a local minimum. However, these gradients can be calculated in parallel. And the power of what we see and the power of these graphic cards, which all these deep learning models are built on, is that this gradient calculations gets hyper-parallelized. And this is what speeded up these neural networks and allowed us to make these deep neural networks architectures. One of the big breakthroughs. So, thank you.